All right, today we're going to look at section 8.5, which is titled Variation Functions. This section is not as closely tied to the idea of rationals of the chapter as the other sections are, but it is related, so it does kind of fit in. But we're going to look at a few different types of variation. We're first going to talk about direct variation. In direct variation, I would explain it as if one thing goes up, one factor goes up, one variable goes up, and the other goes up also, kind of at a constant rate. But you could think of it maybe like maybe your education and your maybe ACT score. So in theory, the more, the further you are along in your education, the more years of high school or of school you've had, or the more levels of math you've had, you would expect to get a higher score on maybe an ACT score. So there's maybe an example. Maybe if you're an athlete, the amount of practice you put in, as the amount of practice goes up, hopefully your level of performance would also increase, things of that nature. So direct variation, let's go ahead and say we've got two things that are vary directly, maybe X and Y. So I could say let X vary directly. Oops, I don't know why I put an R. See there, directly with Y. If that's the case, we can express their relationship as an equation. We could say that X is equal to some sort of constant times Y. I'm going to call that constant K. We will regularly, in this section, use K to represent that constant. It's actually called the constant of variation. So if they vary directly, X equals K times Y. Yes, question. You could use CV. There's no reason why we use the letter K, we just do. It's kind of like M, yeah, just another letter. So our textbook will use the K, we'll go ahead and use the K as well. So let's go ahead and take this scenario, add some numbers to it, and then see if we can use that to predict a future value. So let's say that X equals 6 when Y equals 2. Let's take that data right there. Could we figure out what the K value is, what the constant is? Sure. Let's go ahead and plug those in. So 6 equals K times Y, which was a 2. We can now solve that by dividing both sides by 2. And we see that our constant of variation is 3. And it is a constant, it's not going to change when I'm talking about this relationship. So I can go and substitute that into the equation. So we know the equation that helps us with these particular variables is that X is equal to 3 times Y. And so now, let's go ahead and find X when Y equals 12. So we're doing like a prediction type of situation here. So if Y is 12, what will X be? Well, you could just plug it in. 3 times 12. So we get an answer of 36. Now, there is an alternative way of solving this problem. Our book kind of promotes it. It is more aligned with what we're doing in this chapter, but I also think it's a little bit easier. And that comes if we take this equation and we solve it for K. So if you took X equals K times Y and solved that for K, you would have to divide both sides by Y. And then what you could do there is, because k is a constant and it remains the same no matter which xy pairs we pick, that means that if you have like x1 over y1, it would equal k. And if you had x2 over y2, a different set of ordered pairs, it would also equal k. You had a property in geometry that we could apply here. If x1 y1 equals k and x2 y2 equals k, I can conclude that x1 over y1 is equal to x2 over y2. What was that property called? If a equals b and c equals b, then a equals c. What's that called? The transitive property of equality. That's what we're using here. Because that's true, I know that this situation is true. How would this be helpful on this particular problem? Well, the one set of data, x is 6 when y is 2, that's like your x1, y1. And your second set of data, well, I don't know what this x is. I can call it x2. That's what I'm trying to find. And I know that y2 is 12. If I plugged those pieces of information into this proportion, you'll notice that I don't even have to figure out what k is. I could have just done 6 over 2 is equal to x over 12. We can solve that using cross products, cross multiplication. So this is an equation of radicals. Sorry, not radicals, rational equation. It's why it falls into this chapter. And we could solve by cross multiplying. If you wanted to first simplify this fraction, 6 over 1, you certainly can. 3 over 1. Sorry, 6 over 2 goes to 3 over 1. Cross multiply now. 1 times x is equal to 3 times 12. So we see that x is 36. Didn't we get the same answer? And we did it without having to figure out what k is. Let's take another equation, just another problem just like this. And I think we can solve it probably a little quicker. So let's say, suppose y varies directly as x, and y equals negative 15 when x equals 5. Find y when x equals 3. So I'm going to highlight a key word here. Oops, I didn't highlight. I meant to highlight. The only variation problem we've seen so far, but it's direct variation. That's key, because we will have other variation problems shortly. So it's the same type of problem. I can say, well, I'm dealing with y and x. So y1 over x1 must be equal to y2 over x2. For the same reason we used the letters up above. They gave us y first, that's why I put it in the top. Varies as x, so I put x in the denominator. If we would have switched them around, it would have been fine, but we need to be consistent. But let's go ahead and plug in the numbers. So we have y equals negative 15 when is a key word there. We know that that means the y equals negative 15 and x are 5 grouped together. So that's one of your sets of data. So we can call those y1 and x1, if you will. Negative 15 over 5. And then we have a second set of data. It's an incomplete set. I don't know what the y value is. That's what I'm trying to find. But x is 3. And now I could cross multiply. If you want to simplify first, the 15 and the 5 can simplify. So I get negative 3 over 1. Now cross multiply. 1 times y is y equals 3 times negative 3 is negative 9. So I was able to set up a problem where I didn't even have to find out what k was. You do have to remember, though, that because it's direct variation, we had to divide the y by the x. That's not true of every variation. Let's take a look at inverse variation. Actually, before we do that, I might do joint variation. We'll get to inverse shortly. Let's take a look at joint variation. Joint variation is actually the same as direct, but if there's multiple things that it varies with directly, we call it joint. So it's the same as direct, but really it's multiple direct variations. It's probably a better way to say that, but that's all right. So for an example, we could say, suppose y varies jointly as x and z. Find y when x equals 10 and z equals 5. If y equals 12 when z equals 8 and x equals 3. So I'm going to highlight jointly, but we know that that means the same as direct. We do have 3 variables this time. There's a y, an x, and a z. So give us the y first. So if I set up a proportion, that y1, that kind of looks like an x. Oops, let me make it a little bit. Okay, y1, it varies jointly, or that's the same as directly. So now I move to the denominator, but I put both x and z down there. So x1 and z1. And that will equal y2 over x2 z2. And then I can plug in information. So make sure you identify your 2 sets of data. Find y. So I don't know what y is, but then comes the keyword when. So y is grouped with the x value of 10 and the z value of 5. That's one set of data. I don't care if that's your 1s or your 2s. That's your choice. And then we have a second set of data. If y equals 12 when, so it groups it with the z of 8 and x of 3 values. So we have a second set of data. Those will make up the 2 sides of the equation. It is important that you have that full set of data. Otherwise, we can't solve. So let's plug those in. I'll call the first set of data my 1. So y1, I don't know, over x1, which is 10, times z1, which is 5, equals. And then on the other side, we have a y value of 12 and an x value of 3 and a z value of 8. So if I simplify those, I have y over 50 is equal to 12 over 24. I'm going to simplify the 12 over 24 to just 1 over 2. Cross multiply. Y gets multiplied to 2. 2y is equal to 50 times 1 is 50. Divide by 2, and we see that y is 25. If we chose to use the equation that had k in it, it's not a bad option. Let me just make sure you know what that looks like if it was, since it was a jointly variation problem. You would have said y equals, use your k value, and then times x times z. It would have looked like that. But then we could have plugged in the full set of data to find out what your K is and gone from there. Let's take a look at the inverse variation, because inverse variation is differently. It works differently, sorry. So what are some examples of inverse variation? Inverse means as one thing's going up, the other is going down. Can you think of any examples of something that would be inverse variation? Some of the AP Chem students in the last class came up with one pretty quick. I don't know if any of you are in AP Chem and have a thought of one. As one of your values is going up, the other is going down. Yeah. Yeah, go ahead. Ask your question. Oh, you have one. Sorry, I thought you said a question. Go ahead. Half-life? Yeah, so you're thinking of as time goes on, the amount of it dissipates. That's a good example. We do know that that's logarithmic or exponential, so it's not quite the same idea as something that's linear, but it's a great idea of something going up and down. A lot of our examples aren't perfect because it would be hard to model it the way we're showing here, but that's a good one. What's another one? As one goes up, another goes down. Emma? Pressure and volume. That's the one they came up with in the last class. So as you increase pressure, the volume what? Decreases. Can you think of like what does that look like? If someone's not an AP Chem, they don't know what you're talking about. A syringe? What's that? If you block the bottom and you push, you increase the pressure and there's less in there. Yeah. Good. So that's the idea of inverse, is as one thing is going up, another thing is going down. So let's jump into an example of it. If R varies inversely, as T. Let's stop right there for a moment. I'll continue the sentence shortly. Do you suppose we can set up the equation R divided by T? You think we can say R1 divided by T1 is equal to R2 divided by T2? No, because what does that mean? Yeah, that's a direct. They're both going up or they're both going down. So that's probably not going to work here. That's why we're doing it differently. Any ideas or thoughts on what you would do here? Say it again. Flip them. So T1 over R1? I'll flip one of them and out the other. That's a good thought. Here's how I'm going to propose it. Let's start off with the original equation where we know there's a K value. So it gives us R first. So R equals, we still have a constant of variation. We still use K. Before I multiplied it by T, what do you think I would do here? Divide it by T. So we could have this equation. If you solved that for K, because that's what we did in the last problem, what would you end up getting? Yeah, you would multiply the T, so R times T. So we see that it's R times T equals K, and that means we can use R sub 1 times T sub 1 equals R sub 2 times T sub 2. Now I'm intrigued by, Leah, you mentioned, and let's find out if it works. I think I understood correctly. You were saying that if on one thing we did R1 over T1 and on the other one we switched them around, is that what you suggested? Let's see if that would be the same thing. If you did like a cross multiplication on that, you would end up with the T's multiplied together equal to R's multiplied together. Is that what we ended up with up above? No. So it does get a multiplication idea, but it's not really the same thing. Okay. So we know that this scenario is true, and that allows us to bypass figuring out what K is. But I know if I multiply the two numbers together in one set of data and I do the same thing in the other, it will allow me to figure out a missing piece of information. So let's say Where are we? Okay. R equals -6 when t equals 2. And then we're going to find R when t equals -7. Go ahead and do that. Just a quick raise your hand when you think you have it. See a couple different answers. I don't think everybody has the same one, but what would we get? What would we do with this first set out of the -6 and the 2? Multiply, okay. So -6 times 2. And then we multiply together the other two, R times -7. What do I do here? What do I get for an answer, I should say? Is it negative? The negatives will cancel out, so 12/7. If I had asked what the K value is, if I would have changed the question, say, hey, what's the constant of variation? What would we get? Wouldn't it be -12? R times your T. So -6 times 2. -7 times 12/7. Good. We can have problems that do both direct and inverse at the same time, or joint and inverse at the same time. You can have combinations, bigger combinations of things. So let's do one where we have a combination of both direct and inverse. All for our notes, you should have some time to work on the assignment. So here we go. Suppose f varies directly as g, and f varies inversely as h. Find g when f equals 6 and h equals -5 if g equals 18 when h equals 3 and f equals 5. Okay, so kind of a long problem because there's several variations. But what do you suppose we're going to do with this f1? Notice f varies directly as g and inversely as h. Multiplies to the g, divides by the h. So you said? I believe that's true if we're setting up the problem with the x. We would multiply by the g and divide by the h. In that case, I don't need that subscript of 1. Didn't get my eraser. Okay, so we could set that up But if I want to set up the proportion of the two fractions equal to each other that allows me to bypass the k, you're going to multiply this problem by the h, and then you'll divide by the g, right? So varies directly as g, we end up dividing by the g. Varies inversely as h, we would multiply by the h. Okay, and plug in your numbers. We don't know what g is, but we do know those two things. And then we have a full set of data. We know the g is 18. Let's see, we need our f first, 5, times our h, which is 3, divided by g, which is 18. So negative 30 over g is equal to 15 over 18. I could simplify 15 over 18 to divide them both by 5. What's that? Oh, I wrote 5. Sorry, I see. Yes. Oh, I'm dividing by 3. Yes. Okay, I'm dividing by 3 and gives me 5 over 6. Yes. So I think I said something different. Cross multiplication, so I get 5g equals negative 180 divided by 5 gives me negative 36. Okay, so that's the end of the notes. You can go ahead and get started on the assignment. Good question. What would be if we wanted to find the constant of that variation? Really, k end up equaling the f times the h divided by g. So we could have had, sorry, I shouldn't use the 6. I need the full set of data. I would use this over here. F was 5 times h, which is 3, divided by g, which is 18. So that's the 15 over the 18 simplifies to 5/6. So k would be 5/6.